Well, welcome back. Today, I want to finish up some of these relations that are important for forming equations of motions of Favre average equations. And I believe we left off near 22.33, where we do a relationship between density and velocity fluctuations. And once we get through this rather quickly, then we'll be able to turn to trying to simplify a little bit these compressible Favre averaged equations and energy equation and simplify them a little bit. And then we'll be through the major equation formulations of the class, which I think people will be happy about. But I think this is one of my favorites because it's so important to understand what the governing equations are and what ones are usually chosen for modeling. And you can see some of these are really assumptions. So some of our closures and correlations involve density and velocity fluctuations, which I underlined, and one great law that connects them, as you'll see shortly, is the gas law. So let's look at the perfect gas law for an instance, which is really great for supersonic flows. And a lot of these things, early measurements and formulations, break down for hypersonic flows. So that's why we kind of usually cut off at Mach 5, just as a rule of thumb. So if we take P equals rho RT, once again, P equals rho RT, right there, you see we get a substitution of a bar and a double prime, which you'll remember is a Reynolds average and the associated time fluctuation, equals R, gas time, with density and temperature. We can expand that. And if these fluctuations are small, then rho double prime T prime should be about 0. So we drop that term. Okay, and if we make this assumption, and looking back at equation 2.46, we note that T tilde goes as T bar, which we can use as a substitution. So if we look at P bar equals R T rho bar, we can write this equation here as the following. And I just want to make some notes about it. First, this equation, we can see that in order to find a relationship between the density and velocity fluctuations, given by 2.118, right there, it's necessary to do an order estimate analysis of the pressure fluctuations. So we'll look at the pressure fluctuations. And usually in these types of fields, the pressure fluctuations can be seen and assumed to be isobaric. And of course, the sound fields, that's the noise fields within these highly high-speed turbulent flows, become pretty intense. And you could look at that as a random forcing. So if you look in the turbulent field at the wall or in the turbulence itself, you'll have pressure due to acoustics, and you might also say a pressure of hydrodynamics. And if you look at spectra of these on the wall in high-speed flows and certain frequencies or wave numbers, the acoustic loading is as high or even higher than the actual aerodynamic loading due to pressure, so it's very important. In either case, it might lead to failure of the vehicle. And it's obviously something we need to take into account. So if these pressure fields are relatively uniform in local regions of the flow, we might estimate equation 2.121 as a relation between temperature. Say right there. So if the left-hand side is balanced or isobaric, then we can write the gas law in this way, and we just estimate, it's an estimate, order of magnitude estimate, that the density fluctuations normalized by mean density go as the temperature fluctuations normalized by mean temperature. And above Mach 5, this assumption totally falls apart. So if you're working in the hypersonic world and doing anything with turbulence, this traditional assumption is trash. But it's actually working really well, confirmed by measurements and DNS for flows from, say, Mach 0 to Mach 4. It's a very good assumption. So of course, if your edge Mach number is greater than equal to 5 in a turbulent boundary layer, this doesn't work. And there's been a number of experiments that show this. And edge Mach number of 5. There's a paper by Kistler and Chen, written in 1963, according to my notes, that show these fluctuations in P double prime over P go as about 5% magnitude, which I guess is sort of a industry cutoff for cutting things off. Outside the boundary layer at that Mach number, so you're, say, ME over, I don't know how to write this, maybe at Y greater than delta, this same fluctuations, P double prime over P bar, will be about 1%, and they die down quickly to nothing just once you get into the inviscid airflow. So we're going to have to make this assumption. So if we're going to take equation 1.122 and put it in, what is it, 1.118, right up here, we'll do that substitution. And we will find equation 1.123, which relates density to velocity fluctuations in a correlation to estimate magnitude. And according to the experiments, this is a justified estimate for compressible turbulent boundary layers at Mach numbers up to 5. And that was shown by a fellow named Morkovin in 1961. So that'll be important in our analysis. So there's only one little more before we get into our equations of motion, and that has to do with viscosity. So for perfect gases, mu, which is viscosity, and heat conduction, K, are usually strongly dependent on temperature. For a wide range of pressures. Of course, the pressures wouldn't be a vacuum, and the pressures wouldn't be extremely high, like maybe in an explosion or something. So we'll just say, okay, our viscosity is going to go as the time average viscosity plus a fluctuation, and then we just pull out mu bar, so it's 1 plus mu double prime over mu bar, and we do the same operation with our heat conduction, because these should have accountable fluctuations. So we might model these as saying mu goes as mu bar times 1 plus t double prime over t bar. And the same goes as k. It's k bar times 1 plus t double prime over t bar. And so those are models, and they're highly correlated, because of course viscosity is strongly dependent on temperature. And I think most people have seen Sutherland's law, which relates viscosity with temperature. And there's usually a 2 or 3 equation law. So it's the same type of arguments as Sutherland's paper. Okay, so that was probably the most painful part of looking at these correlations for mass averaged turbulence flows. So let's look at this in the two-dimensional case first. So we'll look at the continuity equation, x moment equation, and these were previously developed in this slide deck of 291 and 292. And we've put in rho equals rho bar plus rho double prime. That's the RANS average. And this form up here of viscosity. And then these equations can be reduced based on all the Prandtl arguments, which are really done for his original 1904 paper. And we talked about them in the previous class. So this correlation here is rho u prime, right? That's the density times the first component of Reynolds stress, and the density times the first off-diagonal term of Reynolds stress. There's no third term because we're in 2 dimensions. Also, we noted in the previous class that the first partial derivative with respect to y is on the order of 1 over delta, and rho bar uv bar is on the order of delta for most of these turbulent boundary layer flows. So that means that these 2 particular terms for, say, viscosity and the Reynolds mass average Reynolds stress, they're going to be on the order of about 1. Right there. So what does this mean? Okay, I got my right page up. So for both of these ratios and cases, we'll assume will be less than 5% for flows where m is less than or equal to 5. So once again, non-hypersonic. And that's just the journalistic or informal definition of what a hypersonic flow is. But it turns out that's another reason why people usually say Mach 5 is instead of hypersonic. These are your fluctuations of viscosity, and your mass-weighted stress are on 5% normalized for less than maximum value of Mach 5. And if you're really, really curious about how this analysis was done in great detail, I'm going to show you the paper. I believe it's Laffer in 1969. You can just Google that with this analysis. It'll come right up. Okay, so now let's look at the magnitudes of, rho double prime v prime, which we haven't looked at yet. So we're going to take equation 1.123, which is rho double prime equals a function of u double prime, if you look back in your notes. And we'll say a pretty tough assumption that u double prime goes as approximately u prime. That's the mass-weighted velocity fluctuations are on the same order as the time average velocity fluctuations. So just assume that, if you believe that. And that's, of course, true as you go to lower and lower Mach numbers. So at high supersonic speeds or hypersonic speeds, that's a bad assumption. Okay. So for moderate Mach numbers, and heat transfer rates, alpha will be on the order of 1, and then u prime v prime with this assumption will be on the order of the boundary layer thickness, and rho bar over u bar will be on the order of unity again. So therefore, rho double prime u prime bar will go as the order of the boundary layer thickness. So from equation 241, and I'll recall here u tilde minus u bar equals rho double prime u prime all over rho bar, and that's barred, will equal rho double prime, I'm going to write over my equation, sorry, u double prime bar over rho. So we can write this equation 1.30 And, oh, I'm missing a bar here. So these are some extra relations we'll need. So what is the bottom line here from these equations? If you looked at them in advance a little bit, and that's why I handed out, this means in analysis for lower speed Mach numbers, we can interchange bars and tildes on U, but not on V, which is the cross-stream velocity fluctuation. This is our definition of relation between U prime and U double prime, right? With mass averaging, you can see therefore U prime bar is on the order of unity, and therefore U tilde of 1 plus U prime bar over U tilde, right? In equation 2.127 is approximately equal to U tilde. Also using the same arguments, which we won't go through, tau bar xy will be much greater than tau bar xx, and rho bar U prime, V prime, is much greater than rho double prime, U prime bar. And these arguments for turbulent boundary layers are all in another journal article by Bradshaw, which was published in 1971. So you can see this is a whole article just on the analysis of this. So taking all these approximations, we can try and simplify our continuity equation and excimal momentum equation for boundary layer flows, which are of course three-dimensional, but they're governed by these two-dimensional Favre averaged equations. And we'll have continuity, right? And you can see the arguments here. We once again have rho bar, right, which is the density, and we have a momentum term. And you might say, oh, you made a mistake with the bars. I did not. This is actually seen as one term, right? One correlation. And this is a separate rho bar, U bar. So watch out for that. When I first saw that, when I was reviewing this material, I thought this might have been a mistake. Consequently, the same X equation term. Something I often note is you'll see that the viscosity term is now within the partial derivative. And most people, when they learn CFD, they set viscosity to constant, but higher speed flows of heat transfer and large temperature gradients, viscosity is highly dependent on temperature. Temperature varies with space, so we would keep that viscosity term on the inside. It'd be awfully easy to just move it outside partial y, but then your results will deviate a lot from measurement. Once again, just like previous incompressible equation, here's our Reynolds stress type term. You can also simplify this. You can take the continuity equation, right, and combine it with 2.134 and move the density term outside the partial derivative. So then you're just looking at a transport equation for velocity. No assumptions, really. Okay? Do you have any questions about those basic steps? And I should have noted, I guess, here, now I define things, that rho v bar can be expanded out this way. So it's really rho bar v tilde, which we'd see up in this term and other terms. Okay. So some interesting notes about the set equations. Oh, and here's the y momentum equation too. You can see it's much simpler. And what do you see in the compressible form for mass-weighted flows? You see a partial p, partial y term. Now, usually in a lower speed flow, which is laminar, or even a high speed flow that's laminar with no curvature at the wall, I could transverse a pressure probe through the flow, and I would see almost a constant pressure. In turbulent flows, the derivatives of pressure normal to the wall are almost non-zero. And that's why this is kept here in this term. And so if you compare this equation to those laminar flow equations at low speeds, this should absolutely be apparent. So that's another big difference I think I see. But you should also note that partial p bar, partial x is usually much bigger than partial p bar, partial y, as a general rule of thumb. So in some cases, you might be able to get rid of that term. So partial P, partial Y is indeed on the order of delta for laminar flows. And that's why it's often neglected. And for turbulent flows, which is a huge difference between the two, is on the order of 1. And so the pressure variation across the boundary layer is on the order of delta in comparison with the streamwise pressure gradient P. And P remains a function of x and t mainly for those lower speed or laminar flows. Okay, so those are the compressible forms. If we make an incompressible assumption again to these governing equations, which I just listed here, this is y momentum, these are the two x momentum equations, and this is continuity, you'll get a really, really simple equation. So incompressible. And you'll also note that in these two equations, 2138, 2139, there's something beautiful that happened. Since it's incompressible, the mass averaging just falls away, and you completely recover the original boundary layer equations for turbulent flow. And if you remember, this is continuity, and then this is x momentum. And what happens to the energy equation in this case? It's decoupled, and we don't worry about it. We can still use a gas law if we want. So let's look at this one. This is partial u partial x plus partial v partial y. You could look at that as mass weighted or time average. It doesn't matter. It's 0. And the second equation here, once again, is your x momentum equation for boundary layers operating on u bar. And you see there's no partial p, partial y term because it's dropped out. It doesn't matter. It's just basically 0 in this formulation. But, you know, this also means that we can have pressure gradients in our boundary layers when you analyze them, which can be taken into account with the composite profiles we looked at previously. This is exactly the Navier-Stokes equations. And once again, remember, there's your extra term. This is your traditional Reynolds stress term. So you see, when I look at these equations, I could almost say, wow, if I had a CFD solver which solves the laminar boundary layer equations, and I wanted to model them and solve them for a turbulent flow, the only difference is this one extra term. And that was really important observation by people like Prandtl and his contemporaries in Germany. And that's part of how he created the first turbulence model, which is a mixing length model. I also stopped here and really paused and looked at these equations for another reason. Because in the third computer project, our objective is to solve these two equations. And so when we talk about the third computer project and introduce it, I'll rewrite these again, of course. And we'll talk about a strategy to solve them in the simplest way possible, without like an iterative method, but with a space marching method. Another thing is if this is a Mach less than 1, the equations are elliptic, meaning that information goes in multiple directions really, and we might have to use a parabolized scheme to march in space, and that will be very helpful. Okay, so we'll come back to these equations later, but we haven't really talked much about the energy equation. And according to our approximations above, we have shown that the double correlation terms involving, say, u prime, v prime, rho prime, e.g., what would they be? They'd be like u prime, v prime bar, etc., are order delta at most, and triple correlations are going to be even smaller. So just doing the order of magnitude analysis, I wouldn't think we have to worry too much about triple correlations if we're forming boundary layer equations. We also shown that terms like, say, u bar go, u bar goes as u tilde, or argued that at least. And it turns out these are good approximations because our predictions agree if experiment. That's always a good check. And that rho v bar goes as rho v tilde equal to rho bar v bar plus rho double prime v double prime, for instance. So before we can go into these energy equation, we first need to make some kind of similar assumption like this, but for h bar goes as h tilde. And if we can't do that, it'd be very hard to simplify things. So here I'll write the equation, and I will substitute in, if I assume this, I can substitute in like h bar plus h prime is equal to h tilde plus h double prime, and substitute in a mass weighting on the left and right hand sides, this form, and I can do that based on this argument here. And you'll see that the two terms on the right-hand side of 241, if we do an order of magnitude analysis using Prandtl's work, they'll be on the order of delta, just as I wrote. And what do we see? Well, we see that rho h double prime bar will go as rho double prime h double prime bar, and they're on the order of delta. So therefore, we would conclude h tilde goes as h bar, according to, I guess, our postulate. Okay. So we're going to try and extend our boundary layer equation using the same assumptions and write a total enthalpy equation. And just like we did in equation 294, and I'm not going to scroll way back. You can scroll back there in your notes to see the original form. And here's our total enthalpy equation. And you can compare that to just the standard one, and you have a few extra correlations. Well, this one here, rho u and rho v, were already in the previous equations. We now have because it's a compressible flow, we have a partial P, partial T bar. That's the change, the time rate of change of pressure in the flow. And then we have these gradients, but ooh, here's a new term that comes up, which would be needed to be modeled, which is a problem. And oh yeah, and we also used Fourier again, heat conduction law. So based on this and the Prandtl number, and looking in, let's see, this term here is what I mean when the second term in the parentheses on the right-hand side of the equation, we can write it in a slightly different form. So this form here, you can rewrite as these terms, and then we just carry down the correlation, and all these terms are the same. So just using definition Prandtl number, this is how you'll see it more in journal articles that I've seen. So it's often convenient in terms of CFD in practical computations to write rho v prime h prime in terms of enthalpy fluctuations. Okay. So how do we do that? Well, we're going to just neglect higher order terms, second and higher, in 227, which, what was 227 you're asking me? Well, that was a term like h prime equals h prime plus u tilde ui u prime I plus 1/2 ui will be prime kinetic energy minus 1/2 of rho ui prime bar all over rho bar. Wow. Okay, so if you do that operation, you'll get 8 prime, which is static enthalpy plus u bar u prime. And once again, I've used u tilde by u bar, which we showed earlier within a boundary layer approximation. So I'm going to take this equation 2.144, and I'm going to multiply both sides by, and this is a typo in my notes, which I discovered this morning, rho bar v bar prime. Oh, that would be a typo too, excuse me. There we go. It will be v prime. And you'll see that in this equation 2.145. So we'll take this expression here, 245, substitute it in 243, and we'll get this nice expression for the time rate of change conservation equation for the Rand's average of total enthalpy. So this is just a general enthalpy equation, and it's much simpler and way easier to use in CFD, but not applicable to hypersonic flows. And what do we see here? Well, we have a Prandtl number once again, which would be maybe 0.90 roughly for turbulent flows, and we have a Reynolds stress term. rho bar times U prime V prime. Same Reynolds stress term as in the original formulation, incompressible flows. Now we make the incompressible assumption. So we can have an energy equation. Well, if we take 2.146 and say rho bar is constant, once again, you'll get 2.147. So this is incompressible, total averaged Reynolds, right? Energy equation, which is very valuable. And it's very, very simple compared to the compressible form. There's also a few other ways to write these equations. You can take this fully compressible form and write it as 2.148, just a little bit of rearrangement, not a big deal. And but what if we want to track other variables like static enthalpy? Well, h bar will go as, or not go as, but equal to h bar static enthalpy plus u bar squared over 2. I'll plug that into 2.146, and I'll use these two other equations. This is x momentum equation. And we'll have a governing energy equation in terms of static enthalpy. Now, what's the difference for solving total enthalpy and static enthalpy in practice? Just the form of the terms on the right-hand side. And I don't think it's like a critical decision. Maybe one is just a little more computationally intensive than another, okay? So it's really up to the user, but if you're using a CFD code, it's nice to know what energy equation you're using. So this is still for compressible flows, which are fun. And if you're an incompressible flow, it's very common to say that terms like rho bar, right, k bar, Prandtl number, and mu are constant. So it's way easier to solve the incompressible flow. Also, in incompressible flows, the terms u bar and partial p bar partial x, and this is a big one, it's the dissipation term, mu bar of partial mu partial y minus rho bar Reynolds stress u prime v prime bar are small. And most incompressible solvers that are going to contain an energy equation like this can account for small changes in these values, but they're really small, and it's way more common for them to be neglected in the solvers. If you think they're small, and they are according to DNS and measurement approximations, you can try and normalize all these equations, because sometimes it's a lot easier to solve equations in CFD using non-dimensional solvers. And one reason that is that way your terms are at least a little bit more on the same order. And so if you have very, very large terms and very, very small terms in a dimensional code, you don't have that problem in a non-dimensional code, and you'll have better stability characteristics. But that's more of a computer science issue. But nonetheless, that's another reason people like to non-dimensionalize their codes. Traditionally today, it's not such a problem because you have such high precision codes. So how would we choose our non-dimensional numbers? Well, you can see what the outcome is in 2.150, but we'll say time goes as t times maybe u infinity over L. Well, you can see L is my length scale, and I have an x and y, so that's easy. I'll have x over L and y over L, where L is some length scale. If we're in a self-similar flow, like a shear layer or boundary layer, what would L be? Well, that would maybe be the distance from the leading edge of your plate to some position on the plate, if it's self-similar. If you use these, then all our other values fall out this way. So you see we have a non-dimensional Reynolds stress. Well, that's a velocity squared. So there's our velocity term, u infinity, right? So u infinity squared would normalize Reynolds stress. And a lot of the older, almost all older CFD codes, which were compressible, use this non-dimensionalization. Otherwise, they would be not giving realistic results because the computers had limited precision. Okay. Anyway, so now we have our particular non-dimensional variables, and we're going to use these definition and put them back into our static enthalpy equation, which is in 2.49 right here. And we can rewrite it as 2.151. So let's look at this. You'll note that these little asterisks are now denoting my non-dimensional variables. One nice thing is it allows a few more non-dimensional numbers to appear. So usually in the traditional Navier-Stokes equations, you can rearrange them. So Reynolds number appears on the right-hand side, and momentum equation is like 1 over Reynolds number. If we do this to the full compressible energy equation, like in 2.151, other non-dimensional numbers appear. They can also be independently found through Buckingham pi theory for particular problems. So it's interesting that they're also appearing this way. I suppose it's not a coincidence because they have such a strong connection to instability theory. But if you look at these, we have one, which is a Reynolds number based on the length scale. And that should have what? A velocity. So we'll have velocity, we'll have a density, and a length scale. And what goes in the denominator? Of course, viscosity. So there's our best friend, Reynolds number based on a length scale. Or if you're in a turbulent flow, you could actually use L and estimate it as the integral scale, the largest scale of turbulence. Okay, and then we have a new number, E, which we'll talk about a little bit more. And that is what we call the Eckert number. And we'll look at that in a second. And that goes as U infinity squared all over, whoop, I wrote it way too big, sorry, enthalpy at the wall minus, well, okay, I screwed this up, sorry, minus the ambient enthalpy. That's an infinity sign. Okay. Ooh, sorry about that. So let's try and understand what this Eckert number means that appeared out of our non-dimensionalization of the energy equation. Well, to do that and have a little more understanding, we'll set the coefficient of specific heat at constant pressure to gamma r over gamma minus 1. That's straight out of your undergraduate thermodynamics class. And we'll look at this form of the Eckert number, which is a little more useful. So I've replaced enthalpy at the wall and the ambient by C sub P at the temperature at the wall minus C sub P at the temperature of the ambient. So that's one step. And I just rearranged these equations. I've took this term out, and so you see it's the exact same equation. I have U infinity squared, and then I pulled out CP T infinity, multiply through, and I have the same equation, right? T infinity cancels, so it's all exactly the same. And now I'm going to replace U infinity and T infinity, right? That's the ambient Mach number, right? Because M infinity equals what? U infinity over C infinity. And C infinity is a function of T infinity. So there's a gamma minus 1 power that comes in there, and that's a Mach squared because I have a squared of the T infinity terms. And now I have this form. So you can see E equals gamma minus 1 M infinity squared times T infinity minus T well, T infinity. So this is very interesting non-dimensional number. So what does it mean? I wrote in my own notes that if the temperature difference is the same order of magnitude as the free stream temperature, the Eckert number becomes equivalent to free stream Mach number. So E goes as to M infinity as delta T is on the order of free stream temperature. So that means this goes true. Eckert number is really only important at higher Mach numbers where you have differences between temperature walls and the ambient temperature. You can imagine at low speed and compressible flows, there's very little temperature difference between the wall and the ambient. Hypersonic flows highly heat the walls, and you have a huge difference between the temperature wall and the ambient static temperature. E is very small, basically goes to 0 as M goes to 0, the Mach number, since the integral Reynolds number is still large. in the boundary layer. So therefore, E over REL would be small. So what does that mean in terms of the equations? Let's go back here and look at E over RL. So that would actually become rather small as your Mach number goes down, and even though Reynolds number is really large. So E over REL goes to 0 as faster, and RE goes to infinity, I suppose. What does this mean? In terms of the equations, is that the work due to pressure gradients will be very small and negligible in terms of turbulence modeling. Okay, so that's the Eckert number. And you can see that it's nothing but a measure of flow velocity with temperature wall difference. And you'll see that come up. It's another non-dimensional parameter which I would recommend to be matched between like wind tunnel flows and flight vehicle flows. Okay, once again, let's make the incompressible assumption. We'll just write, hey, rho bar, we'll just say it's a constant. And we'll get an equation for mean static enthalpy. And here, alpha in this term is nothing but nu over Prandtl number, which I've written here. And you can also write it after you make ideal gas assumption as a function of temperature. So that's awfully nice. If you're an incompressible flow, perfect gas, you can directly track temperature in your energy equation versus something like enthalpy. But then you have this correlation here of fluctuating temperature and velocity. Okay, so those are the major equations for two-dimensional, three-dimensional, mass-weighted flows. So imagine you're in an aircraft company and it's the 1960s or 1970s, and you're starting to get the most basic computers available to you. And your boss walks in and he puts a terminal on your desk. A terminal doesn't really have a CPU and hard drive and local RAM and all the stuff that we have today. It's just like a high-speed connection with a keyboard and a screen that connects to a local supercomputer. And time on that computer is highly controlled. And you're tasked with finding drag and lift and high-speed vehicles for companies like McDonnell Douglas. This is exactly what happened to people in that era, working for aircraft companies, mainly in the United States and somewhat the Soviet Union. And you would probably notice that a lot of your aerodynamic bodies are axisymmetric. So if you were a keen person and turned out to be successful 30 years later and have your name known today, you would probably make some assumptions, like steady flow, you can't make it incompressible, and you would want to develop extremely fast solvers to do these aircraft design. So to do that, almost everybody in the era, because they only had limited computer power and computer time, resorted and made axisymmetric assumptions. And that was a big decision. And even though people had ideas of like high-speed vehicles that aren't axisymmetric before computer era, what would an example of that be? Non-axisymmetric, hypersonic, or supersonic vehicle, what would it look like? It might look like a typical Coke bottle aircraft, or if it was more of a missile configuration, it might look more like a wave rider. So wave riders weren't axisymmetric, and they rode the wave like a shock wave, which created lift. But if you're in the supersonic regime, those things aren't really as useful, and so people really focused on axisymmetric type bodies for analysis, even of full aircraft. And that's why you can also see like a lot of the early supersonic aircraft, like the Bell X-1, had very axisymmetric features, like of the fuselage. The fuselage was very axisymmetric, and the airfoils were very close to diamond airfoils, which are not wonderful supersonic airfoil design. But that's why you see a lot of these aircraft in museums looking like that. And it's partly because people mostly understood through CFD and somewhat the wind tunnel flows of the axisymmetric assumptions, which we're going to look at here. And it has to do with the turbulent boundary layers, because of course that's what's responsible for a lot of the drag beyond wave drag. So these governing boundary layer equations for axisymmetric flows actually look very different from the two-dimensional equations. And so we don't have to do a ton of work to turn our two-dimensional equations into axisymmetric equations, because of course aircraft aren't two-dimensional, and the boundary layers certainly aren't either. And some of the vehicles are very, very thin. So one interesting thing that you can think about is if our vehicle was axisymmetric but huge, like the radius of the fuselage, which was large, you could actually approximate the boundary layer flow with the two-dimensional equations, and that's what people originally did. But of course, if your body becomes more narrow, which is good for aerodynamics, you want something long and slender, then the small radius of the fuselage would have a huge impact in the equations, and you can see that from the equations. So the similarity, 2D equation and the axisymmetric equation are very similar, which you'll see in a second. And if you look at it from a boundary layer point of view, once again, we have a very long, thin aircraft, something like this. Some control surfaces, maybe a little canard. You'll see that there's a boundary layer on the aircraft, and it's on the order delta, and everything out here, right, might be potential flow. So it's the same type of assumptions for boundary layer flow for external aerodynamics. And it's a body of revolution, so if we look down the fuselage, right, we'll have something like phi and r, and phi wouldn't mean anything, right? So there's no azimuthal variation. And that means that most of the flow field, once again, is a potential flow. And we'll argue that all these sort of 3D equation and two-dimensional equation arguments that Prandtl made would be exactly the same. So if we look at a steady flow, it'll be compressible, which I'll just write comp for short, and it'll be turbulent. And we care about lift and drag and basic aerodynamic parameters. And we can take equations 2.133, which is continuity, 2.135, which is x momentum, 2.142, which is y momentum, and 2.146, which is energy. And I'll write energy, y momentum, x momentum, and continuity, which is mass, right? I'm just going to take the 2D equations and do a coordinate transform from, of course, 2D to cylindrical coordinates. It's that easy. And I'll show you what I get. Oh, here's my coordinate system, which I just sort of explained. Phi is azimuthal. R naught is the body location. R is the location of the fluid parcel here. And there's some point P, which we would approximate as y cosine alpha. Now you'll notice something is a little different than straight up cylindrical coordinates. People like Cebeci at McDonnell Douglas did something keen, and that they defined the radius r from some axial position x as the distance from the centerline axis of the axisymmetric vehicle out to the fluid parcel point. But you'll notice that they also define a coordinate y, which is normal to the body up to that point. So that's where this y cosine alpha is coming from. Why did they do that? Because in the numerical CFD solvers, they wanted the grid lines to be orthogonal to the body for the purposes of numerics. And when they do a coordinate transform from physical coordinates to computational coordinates, from x to psi and y to eta, they would have a uniform grid. So it was actually a really good decision because it's more work mathematically in terms of the form of the equations, but it's way easier to program. So that's where that came from. So let's look at the major equations they found. And these are ones that are really basis for most early axisymmetric turbulent models. Here's continuity. All right, so there's our conservation of mass. This is our x momentum equation. And here's our energy equation. Okay. The right-hand side of this energy equation can also be written in other ways. And you'll notice there's interesting little variable here, r of k. R of k RK, RK, and all the equations. So how do they define that? Obviously, if I take R and set K equals to 0, right? So R to the 0th power, what should that equal? A variable to the first power, or 0th power. Unity, right, 1. So you can see if that happens, then all these R to the K's go to 1, and I'm recovering my original two-dimensional equations. If I set K equals to 1, I just have R, and I have the axisymmetric flow. So this was another excellent choice for people developing early turbulence models and codes for axisymmetric vehicles, in that they would have the exact same code. But the input file for the particular case they're running, they would just set 0 or 1 to automatically change their code from 2D to axisymmetric. Indeed, when you look at your contemporary CFD codes, you can often run them in an axisymmetric mode, a 2D mode, and fully three-dimensional. So they'll have to have an axisymmetric form of the equations, which look very much like these, for a compressible steady solver. Okay. And this is a little bit different than what is programmed today, but this enforces the condition of the grid point being orthogonal to the wall at the local surface of the vehicle. And alpha, of course, is the angle of inclination. So what happens when you have a body which has very, very, very sharp changes in it? Alpha might be in the wrong direction of the flow. I mean, certainly that'd be a valid axisymmetric flow to have some like bluff body in the flow. But then by making this choice, they wouldn't be limiting themselves to slender bodies. So you would want to have a general axisymmetric system if you're dealing with like bluff bodies, like a Mercury capsule coming back to Earth. Okay, but a lot of people developing early turbulence models didn't care about the turbulent flow over a reentry capsule. It's all like wake turbulence. And most of the flow over like a reentry capsule like Apollo or, oh my God, are we over time? Nobody said anything. I'm so sorry, I was getting into, well, let me just finish this quick discussion and we'll stop. But next time you say, someone wave at me and say, hey, you're rambling too much. But just think about when you go to a museum like the Smithsonian and look at a reentry capsule like the Mercury capsule that's been recovered, not new. You'll see kind of like a triangulation or zebra striping or cross stitch, like a chessboard that's been stretched on the surface. Those are where the instability waves have left a pattern on the vehicle. They're instability waves. They're not fully turbulent flow. So this whole formulation wouldn't be useful for that anyway, because the flow is dominated by high-speed instability waves. Okay, so this is really an assumption for slender bodies. So for now, I'll just write slender bodies, and we'll leave it there today. And I do apologize for going 5 minutes over. I guess we have such polite students, nobody wanted to interrupt me. I appreciate that, thank you. So anyway, I'll let you go. I hope you have a great weekend.